Before we do chapter 2, let's talk just a little bit about the lab we just did. Can review the principles because we're going to be using these basic skills all throughout the semester. First thing we did was to read volumes. We did this using a small graduated cylinder and a large one. And just to review, what we said was when you read a volume, if you have a negative meniscus, so this is what it's called, a negative meniscus, you read from the very bottom. Now, on this particular slide, if I was to look at this, this is 6, that's 7, 6.2, 6.4, 6.6, that's less than 6.7. Probably 6.62-ish might work. For a reading like this, you can get 3 significant figures. Once again, we're sure it's 6.6, and we guess at the 0.2. With our larger graduated cylinder, again, reading from the bottom of the meniscus, this is 50, 51, 52, so we're sure of 52. And it kind of looks like it's most of the way up here towards 53. We could call it 52.8. Any questions? Now, water and most polar liquids form what we call a negative meniscus, where the water kind of runs up the side of the glass. The reason for that is the glass itself is polar. Silicon oxide, water is polar. Polar molecules tend to be attracted, so they're kind of sucked up the sides. Something like mercury, however, is not polar. It's a metal, liquid metal. And as you see, it forms a negative meniscus, a positive meniscus. And if you have a positive meniscus, here you read from the top. So for the negative, you read from the bottom, positive from the top. Any questions? You did measurements and you had to round numbers. Let's just practice that. Very simple. If we have this as a raw number and we want 3 significant figures, that means we have to get rid of our 9. First rule, very obviously, if it's over 5, next one increases 1, so 5379 goes to 538. Obviously, if it's less than 5, as the 1 is here, it would round down to 241. The thing that people don't quite know what to do with is what if your least significant figure is a 5? Basically, if the preceding number increases by 1, if it's odd, and remains unchanged if it's even. This means that 1775 would round to 1778. This is odd. This is even, and it would go down to 17.6. Simpler way to remember this, that I remember, oops, is shown, come on, right here. The rule is always to round if it ends in exactly 5, so that your final number is even. Any questions? Now, we talked a little bit about accuracy of measurements. Turned out that there are 2 measures that you need to think about. One is accuracy. That's how close your number is to a known number. And the other is precision. That's how close one measurement is to another. This is a dartboard. If we did this, we would have an array that was neither precise nor accurate. basically all over the place. If this was a measurement, they would be everywhere. We're shooting for the bullseye. They're not accurate, nor are they precise. We can have precise measurement that is also not accurate. Usually this is some sort of systematic error where your scale is off or something like that. So instead of getting where you're supposed to, you get this. This is mine, of course. This is both precise and accurate. Precision, we're all in the same spot. Accuracy, we're very close to where we're supposed to be. Any questions? Putting this in forms of a problem, if we had a mass of 25 cubic centimeters of water, and its mass was found to be 24.9, we could calculate the density simply as mass divided by volume. Mass over volume. Our mass is 24, our volume is 25. Do this, we get 0.996. If you look it up, the density of water at room temperature, that's about 25 degrees, is 0.996. So this is a very accurate measure. Now, if we repeated this many times, and we got basically the same number each time, we would have both high precision and high accuracy. We can have high precision with low accuracy. Once again, they're all the same, but they're wrong. We can have an array of data of very low precision, but actually if you take all these numbers and average them together, they're right on the line. So this is, the average value is accurate, but it's a very low precision measurement. And finally, this is just all over the place, low precision, low accuracy. Any questions? We also measure the density of a little lump of something. Remember, density is mass divided by volume. This is 1 cubic centimeter. Very important to remember in chemistry, the relationship between liters and cubic centimeters. If you take 1/1000th of a liter, you get a milliliter. Remember, milli is 10 to the minus 3. And this is exactly equal to 1 cubic centimeter. That's by definition. If we had a chunk of gold, this was 1 cubic centimeter on a side, and it weighed 19.3 grams, mass divided by volume, density of 19.3 grams per cubic centimeter. Also, grams per milliliter, if you wanted to. Same thing. Now in lab, we had a long chunk of metal. Oh, this one is 5.4 centimeters. Each side turned out to be about 1.2 centimeters. We had to calculate its density. First thing we had to do was calculate the volume. Remember, this is length, width, height, to give us the volume in cubic centimeters. Next, we took a mass. Oh, here we go. I wanted to point this out. 7.776. This is what you actually get on your calculator. But all these measurements are to how many digits? 2, right? So they're 2. We have to round this to 2 significant figures, so we would round up to 7.8. All right, to do our density calculation, we weighed the thing. In this case, it weighed about 73 grams. Here's our volume. This is our calculator answer. Again, we must round to two significant figures. Any questions? Density is what's known as an intensive property of a substance. An intensive property is something that is just totally characteristic of the substance. When you take a density, the sample size doesn't matter. The density will always be the same. To show that, what if we had two bars? Kind of put them together if you want. And we weighed them together and took their density together. We would get 146 grams for the sum of the weight, 7.8 cubic centimeters each. So this times 2. We divide. Once again, we get 9.4 grams per cubic centimeter. Doesn't matter the sample size, simply is an intensive property. We also did the cute experiment where we took our stopper, dropped it into something. We measured the initial volume, the final volume, and from that we could calculate the volume of the stopper. Just representative numbers. This is the volume of the water it displaces. Representative numbers, mass divided by volume. Our final and initial values here, this is the mass. Do our division. Remember, we're measuring this in milliliters, but that's the same as cubic centimeters. Our density would be 1.86 grams per milliliter or grams per cubic centimeter. Same thing. Any questions? Grades for the lab will be up on Blackboard as soon as I get to it. So, now, when we did chapter 1, we did metric conversions and stuff like that. I apologized that we did not have a tutorial, and I felt really bad. So bad, in fact, that I went out and I got it working. There is now a tutorial called Simple Metric Conversions. These are simple problems, but they're really good, I think, at helping you formulate ratios and doing the given ratio calculations. You will get your 5 points if you do this 5 times. Okay, a sample problem. Here we have 3.04 grams, and we want this in kilograms. Now, as you look at this, it should jump out at you that this is our given, 3.04 grams. The ratio we want is going to be between grams and kilograms. Now, there are lots of ratios you could write, lots of them. As long as they're valid and gram is in the denominator, that works. This is one set that works. Our given is 3.04 grams. For the ratio, since kilo is 10 to the third, if we multiply that by 10 to the minus 3, that's the same thing as 1. 1 over 1. That works. One more time. We have 10 to the minus 3. Whenever you see the kilo symbol, that stands for 10 to the third. Multiply those together, that's 1 gram. All right, so we take our 3.04, grams cancel, multiply it by our 10 to the minus 3. We get 0.00304. Now you could write it out this way in decimal, or you could write it out using what's called E notation. If the number gets really big and ugly, E notation is easier. This is sample. If we have 10 to the minus 3, you write that in E notation as 1e minus 3, no space. Okay? So this would be 3.04 e minus 3. Now, if you try this and you can't quite get it, click on the Show Answer. Here's your given, here's your ratio, and here's the answer. Isn't that neat? Any questions? All right, let's go ahead and move into chapter 2. Here we're going to talk more about atoms, atomic structure, things like that. Last time, we looked at this little slide where we have the classic depiction of an atom. We said this is wrong, that in fact, electrons are not in little orbits around a nice big nucleus, but in fact, the nucleus is very small. And quantum theory tells us that the electrons are in a diffuse cloud. So it might look something more like this, where the nucleus here is a teeny tiny dot that would be less than 1 pixel on the screen. Now the protons and the neutrons make up the mass of the atom. The mass of the electrons is essentially neutral, 0. We said that in a truly copper penny, we would have 28 sextillion atoms. Therefore, we concluded that atoms were very, very small. Likewise, the subatomic particles are very small. Mass of a proton, we said, was 1.67 times 10 to the minus 4. And then last time in chapter 1, we talked about scientific notation. This is the decimal equivalent. We're moving it over 24 places to get our exponent. The mass of a neutron is essentially the same, and the electron is much, much, much less. The conclusion here, once again, is that virtually all of the mass of an atom is located in the teeny tiny little nucleus and is made up of protons and neutrons. This is the drawing that I made. And like I said, the nucleus would be here and it would be less than 1 pixel. But even that doesn't quite tell the story. To make us a little more dramatic, this is Wrigley Field. This is a golf ball. If the electron cloud for this atom extended throughout the entirety of Wrigley Field, the nucleus would be a golf ball sitting down here on the infield. So again, virtually all of an atom is empty space. Little tiny nucleus, big electron cloud. Any questions? All right, we talked about elements as being the simplest form of matter. They only have one type of atom, and every element is identified by a chemical symbol. We looked at several of these. We arranged them on what we call the periodic table of the elements. And I managed to get the thing pulled down, so this is our classroom periodic table. On a slide, we'll use something looks more like this usually. For the elements, many of them are obvious. H for hydrogen, Be for beryllium, Mg magnesium, C for carbon, He for helium. These are the halogens, a very important group. F for fluorine, Co for chlorine, Br bromine, I for iodine. There are others, however, that are a little more obscure. For example, silver is Ag, gold is Au, lead is Pb, Hg is mercury. Let's see, Co is cobalt, and Cu is copper. Interesting, because there's no U in copper, is there? Likewise, calcium is here. Cadmium, where's cadmium? There it is. Cadmium is here at Cd. There are some that are very important to remember. Sodium is Na, potassium is K. Many of these down here you don't need to remember because I never do either. Let's see, As is arsenic, but Ar is argon, etc., etc. There's a set that we have in the slides called our starter set. We'll see that again in a minute. But before we do, I want to talk a little bit about the periodic table and where it came from. It was actually the original idea of a Russian chemist named Mendeleev. And it was very clever. It was known that elements could react with things like water to form oxides, so they incorporate the oxygen. Specifically, let's look at a group of metals. If we took a metal, reacted it with oxygen, we could form M2O. There were a series of metals that formed oxides with two metals and one oxygen. There's another series that formed one metal with one oxygen, etc. The first series here consists of these guys right here, and we're going to look at lithium, sodium, and potassium. They not only react with oxygen, they also react with water. Now, lithium is up here in the second period. It's a metal, and if you plop it in water, it fizzes, reacts, obviously, forming hydrogen gas, actually, and it's pretty much consumed in a few minutes. That's lithium. Now, in the periodic table, sodium, Na, is underneath it. If you put sodium in water, it gets very hot, so hot that it melts the sodium, forms this little ball, minimized surface area, and scoots around the surface, again evolving hydrogen gas. Finally, this is potassium. It's below sodium. There it goes. Take a little chunk of potassium, you put it in water, instantly it melts. It gets so hot that the hydrogen gas that's formed reacts with oxygen in the air, and you get a flame. So Mendeleev put these things together. These all form metal 2, oxygen 1, and they had different reactivity. Came up with this table. Now we misspelled table, also misspelled group, but he was Russian. But if you look here, we have lithium over sodium over potassium, just like we have on today's periodic table, simply based on the fact that these are R2Os and increasing reactivity. Rubidium and cesium, if you put them in water, react so quickly they basically explode. This is what our periodic table looks like today. It's got 18 spaces going across in the big block here. We'll explain these guys in a couple minutes. And these are all the different elements. And they're arranged by what we'll call atomic number. We'll see in a minute, the thing that defines what an element is its atomic number. That's the number of protons in its nucleus. We'll do that in a second. Periodic table that we will use looks a lot like this, and we're going to divide it up into groups and periods. Groups go across, and even though there are 18 spaces here, we're going to number our groups 1 through 8. Now, the reason for doing that is these are called the representative elements. And when we start talking about chemical bonding, using the nomenclature 1 through 8 will make it very easy to understand how bonds form. Down here we have periods. These have to do with the quantum levels that the electrons live in. Here we have period 1, first quantum level, can hold 2 electrons, 2 can hold 8, 3 can hold 18, 32, etc. Let's just take our periodic table and use it as a grid, just for practice on identifying elements. If I tell you we have something in group 1, period 4, what is it? Well, group 1, so we're starting here. Period 4, we're down here to K. What was K? K is potassium. How about group 2, period 6? Group 2, go down to number 6. We're at Ba. Take a guess what Ba might be. Barium, it is. Think barium enema. Group 8, period 4. We're all the way over here. 1, 2, 3, 4. Kr is what? Think Superman. Not kryptonite, it's krypton. This is our starter list. Again, we use these commonly in class. Kind of make sure you know these. And also, if we happen to mention things, work them in a problem, whatever, know those two. Not going to require you to know everything, that would be stupid, but know the ones that are common. Any questions? Now, there are many ways to test a concept like this. Quite often when we cover a topic like I said before, I will throw out exam questions from old exams. So let's look at some on this subject. Here we're looking for the symbols for silicon, arsenic, bromine, barium, and cobalt in that order. Well, silicon is on our starter list, but we haven't talked about it yet, really. But SN, we did mention, that's 10, isn't it? So that means that silicon must be Si, so we're down to these three. Arsenic, Is arsenic Ar? No, that's argon. Arsenic is AS. So with this one or this one. Bromine, that's one of the halogens. I said these are very important to know. Br, well, they're all Br. Barium, we just did barium. Barium's a Ba. And finally, cobalt. Cl is chlorine. Co is cobalt. Which of these has a symbol with two letters? Fluorine. Fluorine was over here in group 7. The first one is an F. That's a 1. Phosphorus. Phosphorus is right there. It's a P. Oxygen's an O. Nitrogen's an N. Remember silver. Silver was Ag. Gold Au. Na, you never can forget Na. What is Na? Sodium. Copper, chlorine, cobalt, carbon, and cadmium, the C group. Copper, we said, was not Co, that's cobalt, so it's Cu. Chlorine, we said, was Cl, so we're down to these two. Cobalt, we said, was Co. This is calcium, so there's Co. Carbon's a C. That's simple. Cadmium, Cd. That's where we are. And finally, oh, not quite finally, which of these has one letter? We said that iron had Fe, antimony was Sb, tin was Sn, sodium is Na, phosphorus is a P. The one that everybody gets confused is phosphorus and potassium. Which is potassium? Potassium is a K. Any question? Now you might see questions like these, you might not. It depends on my mood when exam 1 comes around. Remember when we have exam number 1, I will give you a sample exam first that will look exactly like exam number 1. Will look exactly the same. Totally different, but it looks the same. We will then go over it in class. And on exam day, you'll see another exam, looks the same, it's different, but it's a very calming effect. All right, elements and atomic symbols. An atomic symbol is something that we will use to denote the atomic number of an element and its mass number. Now again, the atomic number is the number of protons in the nucleus. This is the one thing that defines what an atom is. Carbon has 6 protons in its nucleus. Look at the periodic table here, you see the little 6 above carbon, that's its atomic number. Doesn't matter how many protons or neutrons it has. Doesn't matter how many electrons it has. If it has 6 protons, it's a carbon. The atomic symbol is constructed by taking the symbol for the element. We will then write the mass number. The mass number for that particular atom is simply the sum of protons and neutrons. We will then take the mass number, put it as a superscript in front of the element symbol. Next, we will take the atomic number, we will put it as a subscript in front of the symbol. That is our atomic symbol. Simple to construct. When we do radioactive decay, this will be a very important skill to understand. Any questions? Well, let's do some. We'll do these quickly together, and then you can do some others while I pace. Hydrogen, the symbol is H. Typically, hydrogen will have one proton, atomic number of 1, but no neutrons. So since the mass number is the sum of those two, the mass number is 1. H is our symbol. Atomic number is 1. That's our subscript. And we would write it like that. Lithium, our symbol is Li. Atomic number is 3, so we have 3 protons. That's our subscript. Typically, it will have 4 neutrons. 3 plus 4 is 7. That's our subscript. We would write it like this. Lithium, 7, atomic number 3. Helium, atomic number is 2, symbol is He, so our subscript is 2. Typically, it'll have 2 neutrons, so the mass number is 4, and we write it this way. And beryllium, our symbol is Be. Atomic number is 4, so that's our subscript. Typically, it will have 5 neutrons, so that's a 9 for our superscript. Very simple process. Any questions? The top number is the sum of protons and neutrons. The bottom number is the atomic number, which is protons. All right, go ahead and do these. Our symbols, just to help you out. Oxygen is O, carbon is C, potassium is what? It's a K. Iodine is an I. Our first one is oxygen, that's an O. Atomic number is 8, 8 protons, that's our subscript. 8 and 8 is 16, that's our superscript. Oxygen would look like that. Potassium. What's K? Potassium. Potassium is a K. Atomic number is 19. That's our subscript. Typically 20 neutrons. 20 plus 19 is 39. Potassium, 39. Carbon. Our symbol is C. Atomic number is 6. That's our subscript. 6 and 6 are 12. That's our mass number. That's our superscript. Carbon 12, it's called. And finally, iodine. Our symbol is I. We have 53 protons in the nucleus. Our subscript is therefore 53. Now, I didn't see anybody using a calculator. So what's 53 plus 74? 127. Any questions? Now, in the past, I have asked an exam question, something stupid like, write the atomic symbol for magnesium. Okay? I have done that. But that gets really boring. This is a little more interesting way to do it. I give you that the mass number of argon is 40. I want to know the period, the group, protons, neutrons, and the atomic symbol. Now remember, on the exam, you will have a periodic table that will look just like this. So it'll have everything on it. So, step one. We're talking argon. Where is argon? It's there. What's the atomic number? Well, first of all, what's our period? 1, 2, 3. What's our group? 8. Now, what's the atomic number? Squinting it, you can see it. It's 18. 18 protons. So if the mass number is 40 and 18 of those are protons, how many neutrons? 40 minus 18 is 22. And now very quickly, write the atomic symbol. AR is our symbol. 18 is our subscript. 40 is our superscript. And that's what you have. Any questions?
You have to put the numbers in before the letters.
Yep, before the letter. It's impossible to do in a word processor.
Okay.
Makes it very frustrating. All right, go ahead and do this one on your own. This is actually the one that was on the exam. The other was just an example. Neutral element with 12 electrons and a mass number of 24. So you're sitting here scratching your head, sort of, and saying, what the heck is the element? We can't do this if we don't know the element. In order for an element to be neutral, it must have the same number of protons, which are positive, and electrons, which are negative. If this element is neutral, and it has 12 electrons, how many protons must it have? 12. Go ahead and finish it. Magnesium is in the 1, 2, 3, third period, right? Likewise, it's in group 2. If its mass number is 24 and 12 of those are protons, how many neutrons? 12. 12 and 12 is 24. And the atomic symbol, Mg, our subscript is 12, our superscript is 24. Any questions? Now, it's an important skill to be able to take an element and figure out how many protons, neutrons, and electrons it has. We'll use that skill throughout the course. Therefore, there's a tutorial. It has an odd name. Atomic configuration of elements and ions. So this is the one we're talking about. I tend to just call it lovingly protons, electrons, and neutrons. All right, this will come up. It's a table. Sometimes the symbol will be here, sometimes it won't. You can click on this button and get a periodic table if you want. There's also a periodic table you can print on Blackboard. That's the same one that we'll use on the exam, if you want to get used to fiddling with that one. All right, SN is our symbol. What is SN? You've seen it 3 times, 4 times today. It's 10. And where does 10 live? Down here somewhere. There it is. Okay. We look at this. What is the atomic number of 10? Squint it out. You can see it. Your eyes are better than mine. It's a 50. Number of protons, 50. We're given that we have 66 neutrons. So what's our mass number? 50 plus 66 is 116. Now our charge is +1. When you enter things like charges here, you can enter -1, -2, whatever, that's good. Don't use the plus sign though. They won't be able to figure that out. So just 1, 2, 3, whatever, okay? Our charge is +1. Remember, +1 means it has one more positive than it does negative. if we have 50 positives, 50 protons, how many negatives? 50 minus 1, 49. Again, show answer will tell you all of this. Go ahead, do bromine. Bromine is in group 7, right there. Again, group 7 is here, bromine is here. The atomic number is 35. That means we have 35 protons. If we have 44 neutrons, the mass number is 35 plus 44. That's 79. And finally, if our charge is minus 1, that means we have one more electron than we do proton. We already know we have 35 protons, therefore we must have 36 electrons. Let's do one more. U, who is U? U is uranium. Do you see uranium anywhere? No. No, it's not in our abbreviated table here. See those things on the bottom? That's where uranium lives. So uranium is all the way down here. Now, in a few minutes, we'll explain why these are at the bottom. Mostly because nobody cares about them. But uranium is here. Atomic number of 92. All right. Atomic number is 92. We have 92 protons. If our mass number is 235, uranium-235 is the isotope that's used to make bombs. It's the fissile isotope. So 235 minus 92 is what? I can't do that in my head either, but it's 143. Now in this one, you are given that it has 92 electrons. We know it has 92 protons, so what's its charge? If protons and electrons are equal, it's a 0. Any questions? Do this, 5 points. All right, just now I said that 235 was the isotope of uranium that undergoes nuclear fission. Very highly sought after. If you happen to have, 35 pounds of uranium-235, you can assemble a nuclear weapon in your basement. I would not recommend it, but you can. It's trivial. It is so simple. Okay, highly sought after. But what is this word isotope? Well, let's go to carbon. Typically, carbon will have 6 protons and 6 neutrons. We'll see in a little bit later that the 6 electrons are distributed around carbon in 2 layers. Now, if we find carbon on the periodic table, you'll see it's in the second period. Remember I said that was the quantum level. Each of these represents a quantum level, the first and the second, but that's for later. All right, 6 protons, 6 neutrons. If I asked you to write the atomic symbol, everybody in the room would write that. Okay? No problem. Carbons are symbols, 6 protons, 6 and 6 is 12. But, remember I said that the thing that determines whether this is a carbon or not is the number of protons. Neutrons don't matter. Electrons don't matter. Just protons. So if I took this nucleus and I added another neutron, I would get a carbon with a mass number of 13. It's still carbon, but now it weighs 13. I can do this again. Put another neutron in there. Carbon 14. These are what are called isotopes. Virtually every element, in fact, every element that is known, exists as a series of isotopes. They all have the same number of protons in the nucleus, but they have differing number of neutrons. Now, this is a little bit of a problem if you're going to do quantitative chemistry. Because if you take carbon, dig up carbon from the ground on Earth, it's going to be a mixture of carbon 12, carbon 13, and a minuscule trace of carbon 14. If you want to do quantitative chemistry, how much does carbon weigh? Doesn't weigh 12, doesn't weigh 13, it's a weighted average. In order to figure that out, you need to know what the, quote, natural abundance is. That simply means of the carbon on Earth, what percentage is carbon 12, what percentage is carbon 13, and 14. For carbon, it turns out about 98.89% is 12, 1.1% is 13, carbon 14 is so minuscule you can't even measure it easily. So to calculate the average mass, what you would do is this calculation. This is the fraction of carbon that is 12, that's percentage times 100, times mass. Add that to the fraction that's 13, and you get 12.01. So a little more than 12. If you look at your periodic table, 12.01, that's the atomic weight of carbon. It's the average of all of the isotopes. If you look everywhere on the periodic table, nobody comes out even. They're all a mixture of isotopes. Get the question. Well, one question that you should be thinking of is, how in the world do you know that carbon is 98.89% carbon 12? Turns out that you can do this using what's known as a mass spectrometer. Big ugly machine. Basically what you do is you take an element or a compound and you ionize it, so you give it a charge. This little ion beam that you create goes into a magnetic field, very powerful magnet, sitting here. The magnet, because it's charged, will bend the path of the particle. The heavier it is, the less it's bent. Lighter particles are bent a lot, heavy particles not so much. You record these at various points, put them into a plotting thingy, and you can measure very accurately the mass of every one of these particles. Example here, this is for boron. Boron, 80.2% is boron 11. 19.8% is boron 10. What I want you to appreciate is look at all these significant figures. I mean, chemists are really good. We're really good at stuff like this. Tremendous. So this is how you get the numbers anyway. Any questions? Another question you might be asking yourself is why doesn't boron 11 weigh 11? Or boron 10 weigh 10? This is something nobody likes to talk about. But turns out that different elements, protons and neutrons will have very slightly different masses. Now, how they know, we don't know, but they have very slightly different masses. So once again, virtually nothing comes out in integer. All right, let's talk a little more about our periodic table. This is colorful, this is not. The one on your exam is not. The bluish things here, all of these things shown in blue, are what we refer to as metals. Metals as a group have certain physical properties. They're very malleable. That means you can smash them down and spread them out, make them thin, make them fat, whatever. They also conduct electricity, and they have several other things. But these are all metals. Over here in this corner, we have what are known as the nonmetals. Nonmetals do not conduct electricity. They're insulators. Nonmetals are typically brittle. They're not malleable at all. The little green guys here between metals and nonmetals are called the semi-metals. They have properties of both metal and nonmetal. The most important property, these are conductors, these are insulators, these guys are the semiconductors. Silicon, germanium, the classic two semiconductors. They are semi-metals or metalloids. Now, as we look at this table, these guys that we've put in our main groups here are referred to as the representative elements. It's old nomenclature. I will never call them that, but you could read it in lots of places. Originally, the representative elements were the things that were typically found in living things. These guys were not. That's wrong. Vanadium enzymes, chromium enzymes, cobalt, all of these are very important in biological systems. But, again, this is historic. These guys in between the representative elements are the transition metals. Just like the semi-metals are a transition from metal to non-metal, these guys are a transition from group 2 down here to group 3. in many of their properties. These guys are also transition metals. They're called the inner transition metals. Now, why are they stuck down like this? Actually, they belong right here, after lanthanum and actinium. These are called lanthanides and actinides. So if we took these and we stuck them here where they belong, the periodic table would look like this. Now, this puts everything in its place very nicely, but it's an ugly table, way too long. Nobody cares about these things much anyway. So we just take them out, stick at the bottom, page holds periodic table very nicely, and this is what we have. Any questions? All right, within the groups of elements, these guys in group 8 are referred to as the noble gases. They're also called the inert gases. Inert gases basically means they don't do anything. They don't react. Now again, that's wrong. They do react. You gotta be really clever to do it, but yes, they do react. We'll see some of the compounds later, but in general, they don't react. They're called noble gases because their ability to do anything evil. Next to them, we get the halogens. I mentioned those. These are a very important group. Make sure you know all these elements: fluorine, chlorine, bromine, iodine. We'll use them all the time. Over here in group 1, alkali metals. We've seen lithium, sodium, and potassium and the way they react with water. Same thing with rubidium and cesium. Thing to note about our first period here is hydrogen is there, but it's actually a non-metal. Now, we'll have a rule about when hydrogen's a metal or a non-metal later on, but typically we're going to consider it a non-metal and all the rest of these metals. These are also called the alkaline earths: beryllium, magnesium, calcium, strontium, barium, and radium. We will use those a lot, the ones on the top especially. Any questions? Now, there are lots of ways to represent the periodic table. We'll see a bunch of representations as we do slides. Again, this looks a whole lot like what you'll see on the exam. Here's another one that doesn't look like anything, but it's a valid periodic table. Here are the inner transition metals stuck down there. Again, a very interesting presentation. Any questions? Questions here? Exam questions. We have an atom of phosphorus. What's the symbol for phosphorus? Phosphorus is a P. Potassium is a K. Last semester, there were people that were still missing that on the final exam. All right, phosphorus has an atomic number of 15, mass number of 32. How many neutrons is this? Well, remember the mass number is simply the sum, right? So 32 minus 15 is what? 17. Here we have neutral, bromine 79. Which of these is true? How many protons does it have? Remember, the subscript is the atomic number. That's the number of protons. 35. A, B, or C, or the dreaded none of the above. How many neutrons? 79 minus 35 is what? 44. A, B, and C. How many electrons does it have? If it's neutral, protons must equal electrons. 35 electrons.